To round out our treatment of the integral test for section 11.3, we're going to talk about the remainder estimate. And it's our objective in this video to introduce and apply the remainder estimate. And before we get into that, let's talk about a series that we already saw. So we know that the series of the inverse of cubes, squares, converges by comparing it to the improper integral from 1 to infinity of dx over x squared. But this integral equals 1, and this series equals pi squared over 6, which is roughly speaking 1.6449, and so on, right? It's an irrational number. So we're never going to get a very precise decimal representation unless we go really, really far out. But what gives, right? What's the difference here? Why the discrepancy, right? We also saw that we can deliberately overestimate and underestimate the sum using integrals. So let's make this precise by talking about remainders of series. So the idea is we're going to write Sn for the nth partial sum again. So to remind you, S of n means we're going to add up the first n terms of the series, and S being the, if we assume that the series converges, is the limit of the sequence of partial sums, right? And this is the actual value of the series. So in the case of the previous example we looked at, right, pi squared over 6, whatever that value happens to be, right, that we're talking about, we may not know what it is, but we know that it exists if the series converges, right? So S sub n, in other words, S sub n approaches S, never necessarily getting there, okay? But we define then Rn to be the remainder at the nth term of the difference between the actual value of the series and the partial sum. Specifically, we want the actual series to come first, because if we write this as the sum from k equals 1 to infinity of a sub k minus the sum from k equal 1 to n of a sub k, what we're really saying is this is the tail we're looking at from k equals n plus 1 to infinity of a sub k, okay? In other words, in the pictures that I was drawing in the previous videos of the series as a sum of blue rectangle areas, right? What we're looking at in the remainder is the part that's not shown. It's the tail of the series. It's the part all the way out in the end, okay? But the tail, then, is you can think of as also the error in approximating out to the nth term. So if we truncate a series to, let's just, for visual representation, think about, a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, and dot, dot, dot. And we know that it goes on forever, right? We stop right here, okay? And whatever we have at that point, that's going to be, we're going to say that's as close as we're going to get. Then the remainder estimate gives us a very nice set of inequalities that bounds the remainder, and as a consequence, it's also going to give us a really good estimate for the sum of the series itself. So let's get into it, right? What is the remainder estimate? So if the series converges, or this only applies if the series converges, then we have a lower bound and an upper bound on Rn. So the remainder, the difference, the tail, right, has to be between the integral from n to infinity of f of x dx and the integral from n plus 1 to infinity of f of x dx. Assuming the same idea where f is the corresponding continuous function to a sub n, right? So why n plus 1 on the left and why n on the right? So visually what we're saying is you can imagine, so I'm going to draw my rectangles again. Sorry for the terrible pictures, but I'm trying my best, I promise. They're not so bad. My pictures aren't so bad. Let's say we're going to stop right here. So then the actual remainder is the infinite sum of all these tiny, tiny rectangles, right? Which is getting smaller and smaller, and if it converges, it is finite, okay? But the over-under on this, so to speak, is remember that we did two things. We set up a ceiling. So this series represents a ceiling on a function, and it also represents a floor. Now it's the same function, just shifted by 1. Okay, one's an overestimate, one's an underestimate. And that means those corresponding integral areas, right, are going to give us an underestimate. But they're going to be, the integrals have to be from a different perspective. So you see how I shifted 1 by, so this is a shift by 1, right? Shift by 1. That's this. Do you see that? So the areas here, they're represented by a shift by 1, and that's what the lower terms are giving you. Okay? So another helpful view of this is because r sub n, the remainder, is the difference between the series and the truncated series, we can do a little bit of algebra to say that the actual value of the series is also wedged between two values, okay? Specifically, the nth partial sum plus the n plus 1 to infinity improper integral, okay? And between the nth partial sum plus the integral from n to infinity of f of x dx, okay? So these are the same, discrete sum. This comes from the actual series. This piece, on the other hand, right, represents the the continuous overestimate and this piece represents the continuous underestimate. I can't spell. So you get out to a certain term, and you'll know that the remainder, so the tail of the series, is going to be between these two values, right? And so in applying this, we can get an approved estimate for a series as long as we go out to we go out to the nth term, and then we perform improper integrals, okay? So I'll leave it at that. Just know that the power of this is integration is easy. Finding the sum of a series is not.